Morning class and welcome to today physics 4B. Today is going to be the second part basically of the lecture that we started last time. We're still dealing basically with Maxwell's equations in free space, meaning that we don't have any charges, we don't have any currents, and we're trying to solve this equation basically in general. It turns out our choice of the solution, because we chose an electric field pointing in a specific direction, that is actually called the polarized electromagnetic wave at the end is going to be a wave. So it's going to be known what is known as a planar solution. So that's the easiest one to do, and that's actually what we're trying to do now. And once we find it, we're going to jump in right away into the problems. So hopefully we can cover at least several problems that are of interest. Now, excuse me. You have a few, I think you have 2 quizzes covering the last chapters from this class. So please take care of them. Those quizzes are part of the overall basically grade. Remember, quizzes count about 5% or count 5% of your overall grade. Also, we still have exam 2, which is the second midterm, which is going to be Thursday, week from today. And I want you to really pay attention to the process, because this is going to be an online exam, which is probably going to be open for 12 hours, starting from 10 o'clock in the morning until like 10 at night. You will have an hour and a half to do the problems, plus half an hour to upload your work to Canvas. So if you're really, I know if you have the special needs, I'm going to take care of that too, but you have to work out within that frame of reference. You cannot really start the exam and go somewhere else and come back trying to finish it. No, it's not going to work that way. The minute you open it, Canvas starts basically counting the time for you. If you don't submit it by the allotted time, in this case it's going to be 2 hours, because you have an hour and a half to do your problems and then half an hour to submit it. Then in that case, it's going to submit it on your behalf and it's too late. If you have problems during the exam, you need to let me know immediately. Okay, you need to basically let me know, and then you need to upload your work. Then if you cannot upload it to Canvas, you have to basically take a picture with your phone and send it to me. It has to be done within the allotted time, otherwise your work is null and void. So this is basically in terms of the process. I'm going to follow up this one with actually communication detailing the process. You can basically you can work with your pencil and take pictures, or you can use a Word document and submit that, whichever is easy for you. But you need to refer to the exact problem and the exact question from the problem. You have to, hopefully you still have those 6 steps basically for problem solving. I know 2 of them are not relevant when it comes to exams, namely basically identifying what is given in the problem, what is asked in the problem, finding the relevant relationships, whether mathematical or physics or geometry, that you need, solve the problem, justify the solutions. Justify the solution or the steps is not necessary for this exam, but in general, it's a good thing to have in mind. Then also at the end, answer the problems, and once you answer the problem, answer the questions that are asked actually in the problem, at the end of the day, you're supposed to have a discussion. Again, it's not required for the exams. You should have taken those papers when we met last time, when we did the on-campus exam. You still have those papers. If not, please let me know, and I probably will share them on Canvas anyway, so that you can have them, so that you know. Because I'm going to go through those grades, because if you miss a question of calculation or some problem, and then that question is needed down the road, you don't want to be in double jeopardy, in a sense that you already lost points for that. You're not going to lose it again. And besides, you could get a lot of credit just by showing your work. So you have to show your work, in other words. Don't forget the units. So this is basically in a nutshell about the exams. There will be a final, and at this point, the final is still scheduled to be on campus, unless I know otherwise. So we're still meeting for the exam on the 8th, I think it's scheduled. So unless they tell us we cannot meet on campus, in which case we have to do it on Canvas, and it's going to follow the same format as exam 2. So this is in a nutshell everything. Don't forget to have a lab that is due this Friday too. I mean this Saturday, I'm sorry. Okay, so this is basically in a nutshell what's going on in terms of organization and where we are and things like that. So let's jump in, finish the class, and hopefully get some problems down the road. it may take a little longer than the normal hour and a half. And the reason why I'm thinking that is because I don't know if it's really wise to return back in the afternoon just to finish one problem or something. So we'll see. Okay, let's get going. So let me share with you screen. Let me bring this closer in here. So, am I sharing my OneNote thing, chapter 32?
Yeah, it's right there. We can see it.
Okay, very good. So, last time we stopped when we were basically setting up the equations. Here are the equations now. We are in free space. We don't have any rho is equal to 0, and we don't have any j is equal to 0. So we are completely in free space. So there is a source of some electromagnetic waves down the road, and now the waves have reached this point in space where there is nothing, okay? So we want to solve it. We chose an electric field that is pointing in the x direction, okay? The fact that it's pointing the x direction, that means this, remember the divergence is the derivative with respect to x and y and z. So that means that the derivative of Ex with respect to x plus the derivative of 0 with respect to y plus the derivative of 0 with respect to z, because the y component is 0 and the z component is 0. So that means this whole thing is equal to 0 according to this equation. But that means that Ex does not depend on x, end of the story. Ex is not a function of x, because its derivative with respect to x is 0. That means it's constant with respect to x. That means it still can depend on y and z and t, but not x, because once you take its derivative with respect to x, it gives you 0. I'm going to make it another simplification here, and that is required that the wave actually travels with respect to z direction. In other words, the derivative with respect to y also are 0. So anytime we will see the derivative with respect to y, we're going to say it's 0. So in this case, all I have is an electric field that depends on x. If I look at this equation, any of these two equations, E here, at the end of the day, basically E is written as Ex, which is function of z and t, in the I hat direction, end of the story. So that's basically what this whole requirement is saying now. We have an electric field that is polar in the y direction and traveling in the z direction. So it's points in the x direction, but it's moving in the z direction. So that's basically what this whole thing is saying. And time, of course, is a factor. If I take its derivative in here with respect to time, I will end up with a function that depends on z and t only. That means the magnetic field also does not depend on anything but z and t. So that's what this whole thing is saying. The same thing in here, the derivatives in here, remember the curl is the derivative with respect to x, the derivative with respect to j, and respect to, y, and respect to z. But then the only thing that is going to survive in here is the derivative with respect to x, because this function depends only on, with respect to z, because this function only depends on z and t. So at the end of the day, this function also depends on, so B immediately, as a consequence of this statement in here, B also is some function at this point, some vector that depends only on z and t only. It cannot depend on anything else. Furthermore, this indicates that E and B are perpendicular to one another, because when I do the cross product in here, the result of the cross product is a function that is perpendicular on both of them, especially the vector E. So B and E are perpendicular to one another. That is one thing. The other thing in here is that B and E are perpendicular too. So it says in here that B and E are perpendicular, so B cannot be in the x direction. As a matter of fact, it has potential to be in the y direction or the z direction only, because of these two equations. It's saying that E and B are perpendicular. Both of them are saying the same thing, that E and B are perpendicular. Because the electric field, I chose it to be polarized in the x direction, that means B cannot be in the x direction. It can be in the y direction if you want to. It can be in the z direction if you want to, or a combination of both of them, meaning in a plane perpendicular to the x-axis. That's all this two equation is telling me. However, this equation is telling me something else too. And let me see what that equation is saying. Remember, the derivative with respect to x is 0. of B, which is 0 anyway, with respect to x, and this does not depend on x anyway, and it's 0, plus the derivative of by with respect to y, plus the derivative of bz with respect to z also is equal to 0, and it's coming from this equation. This is actually the same equation written this way. However, this derivative is 0. Why is it 0? Because this b does not depend but nothing on z and t. Actually, the entire b depends on z and t only. So if I take this b, the y with respect to y, that's going to give me 0. So the only thing that's going to be remained at the end of the day is the derivative of bz, which is, I remind you, is a function of z actually and t, with respect to z is equal to 0. And the only way this could be true if bz actually does not depend on z, or bz is actually equal to 0. That is the only obvious solution, because if I make this 0, and I have to make it, I'm sorry, if at the end of the day this derivative is 0 and this derivative is, so that means this derivative is 0. Since I am far away from any source, that means this bz is constant with respect to, does not depend on z at the end. Then at the end of the day, the only obvious choice for me is bz equal to 0, because I am far from the source of the wave, the source of the disturbance, far from the source. Because, and at that point there is no electric charges and there are no electric currents. Therefore, the only choice in here, because I am far away from them, I am at infinity actually, then in this case, hey, bz has to be taken to 0. So at the end of the day, this is how it looks like. E must be in an x direction, and under these conditions, because we chose it so, and we chose that E actually depends only on z and t at the end of the day, because it has the potential to depend on y. So at the end, we took it only, in other words, which way the wave is moving, call that the x direction. Which way the z direction. Which way the disturbance is going, that is your z axis, okay? And the z-axis must be perpendicular to the other one because of this equation at the end of the day, okay, for the electric field. So at the end of the day, basically what we end up with, and the B field now, because of this choice, also must be a function of z and t, and cannot have an x component because of these two equations, okay? Furthermore, cannot have a z component because of this equation. So at the end of the day, B is only in the y direction. So this is the picture that is emerging from here. You have E in the x direction, and that's it. It's going back and forth in the x direction, basically. Whatever it's doing it only on this axis. You have B that is doing things in the y direction. So this is the y direction. This is the x direction. And both of them, as they are doing that, they are traveling in the z direction because they depend on z and t. So they're going in the z axis. So this is basically what the picture is emerging. So let's now rewrite. So these two equations now are perfectly satisfied. So the only two equations are this that needs to be rewritten. Let me write the curl then in this case. Remember the curl of any vector. And I'm going to write this vector, the curl of, let's call it the vector C, for example, okay? Because we need the curl of A, the curl of E, and the curl of B in this expressions. So let me write the curl of any vector C, and then see what that is. So the curl in this cance is this determinant, I, J, K, if you guys remember from your classes. So this is 0, this is 0, because there is no derivative with respect to x and y. This depends only on z. So that is the only derivative at the end that is going to remain. At the end of the day, both of these vectors, B and E, they don't have the components along the z direction. So I'm going to call that component 0. But one of them has a C component in the x direction, and one of them has it in the y direction. So as I'm trying to write this one in general form, so it's a good idea to write it this way. So let's look at the x component of this vector. The x component is this determinant, okay? And at the end of the day, the x component of this vector is going to be basically the derivative of cy with respect to z in the I hat direction with a negative sign, because you have to subtract the other term, okay? Now the components in the j hat direction. The components in the j hat direction is this derivative minus this derivative, but there is a minus in here. So it's going to be a positive the derivative of Cx with respect to z in the j hat direction, plus the last derivative of the components in the k hat direction is going to be 0 and 0, so it's going to be 0 in the k hat direction. So this product in here, because of our choices, where C represents either A or B. Either E or B, okay? And E has only this one component in the x-axis. If I do that, that means I retain this value only. If I do it for B, that means I retain this value only, okay? Because B has no component except By. So let me rewrite this equations now. Since this component is for E, and E is along the x direction, then in this case, that's the only one that is going to survive, and this is going to be in the j hat direction. So that's going to be the derivative with respect to z of Ex. So that's going to be the derivative of Ex with respect to z. So that's the entire curve. Everything is gone in the j hat direction, if you like, okay? And then must be equal to, according to this equation, negative of the derivative of B with respect to T. And B has only the j hat direct component only. B has only By. So it's going to be minus the derivative of By with respect to T in the j hat direction too. Both of them are in the j hat direction. Actually, I did not need to write the j hat because the B is in the j hat and the cross product is in the j hat, and the j hat cancels the j hat. So this is equation 1. That is the only equation that is remaining from this up to this point that we need to work with. Now we have to do the same thing. Now B has only a y component. That means since it's a y component, I have to retain this component. So it's a negative. The derivative of By with respect to z in the I hat direction. Remember, this has only an I hat in it, okay? This must be equal to mu naught epsilon naught, the derivative of E with respect to T. And E has only an X component. So it's going to be positive mu naught epsilon naught, the derivative of Ex with respect to T. And that is actually in the I hat direction only, because there is no other components for the electric field. So at the end of the day, this two also cancel, and this equation becomes equation 2. So those are the two equations that we have. Here is what we need to do now. We're going to take equation 1 and take its derivative with respect to z. And take equation 2 and take its derivative with respect to t. When I take the derivative of z in here, it's going to be the second derivative of Ex with respect to z. So it's going to be the derivative of the derivative, which is the second derivative of Ex with respect to z, is equal to, on one side, negative, I have the derivative with respect to z of the derivative with respect to t. So it's going to be a mixed derivative, actually, of the two components. The negative, the second derivative of b, remember, b has only a y component at the end of the day, of the derivative of, with respect to z, of the derivative with respect to t. So this is a mixed derivative because I took it's the derivative with respect to t already to begin with, but I'm taking its derivative with respect to z. Okay. Did you guys do partials yet in math or not yet? Partial derivatives or not yet?
Yeah, I've done partial derivatives.
Yeah.
Good. So this is just something that is basically the taking the second derivative, but you have to be mindful of what variable you're doing it. In here, it says the derivative with respect to t of this everything. This is already the derivative of By with respect to z. So it's going to be the mixed derivative again with a negative sign. So it's going to be the negative, the second derivative of By with respect to t, but after taking it with respect to z, is equal to mu naught epsilon naught times the second derivative of everything in here with respect to t, because it was already the derivative with respect to t. So it's going to be mu naught epsilon naught, the second derivative of Ex with respect to t. Now, this is you take the derivative of t first and then with respect to z, and this is you take the derivative with respect to z and then t, but z and t are independent variables. So the order of the derivation really does not matter because they both vary at their own independent way. So you can vary one and then later vary the other because they are not function of one another to be worried about the chain rule or anything like that. So in this case, these two terms must be the same because you have the minus, you have the minus. The order does not matter for similar derivatives. Then at the end of the day, this term must be equal to that term. So this is the equation that we end up with, is the second derivative of Ex with respect to t is equal to 1 over mu naught epsilon naught, the second derivative of Ex with respect to t. That is a wave equation. This is what we learned from physics 4C. A wave equation, this is from chapter 17, and a wave equation whose speed squared is equal to this value. The speed of the wave squared is equal to 1 over mu naught epsilon naught, this quantity. In other words, the speed itself is equal to 1 over square root of mu naught epsilon naught. Let me remind you of some values. We know that mu naught is equal to 4 pi 10 to the negative 7 in SI, whatever units of SI, meter, kilogram, and second, and ampere, and everybody else, okay? Epsilon naught, or 1 over 4 pi epsilon naught, was 9 times 10 to the power 9, basically. I know it's 8.99 something, okay? 8.95 something, okay? So in SI, slightly less than that. It's also in SI. So that means if I take these two numbers in here, that means epsilon naught from this expression is equal to 1 over 4 pi times 9 times 10 to the power 9, okay, in SI. So if I take these two numbers and multiply that by them, and by them one by one, this is what they give me. So mu naught times epsilon naught is equal to, first of all, mu naught is 4 pi 10 to the negative 7, 4 pi 10 to the negative 7. And epsilon naught is 1 over 4 pi. So the 4 pi cancels the 4 pi times 9 times 10 to the power 9. Cancel the two 4 pi's. So if I bring this downstairs, it's going to be 10 to the negative 7, becomes 10 to the positive 7. So the whole thing becomes 10 to the power 16. So remember, I need the square root of this number. So 1 over mu naught epsilon naught, you invert it one more time. It's going to be 9 times 10 to the power 16. If you take the square root of this to find how big the speed is, so this speed must be then equal to the square root of 9 times 10 to the power 16, and that is actually the speed of light. That is 300,000 or 300 million meters per second. This is c, the speed of light. So these waves, apparently, they are, and when compared with the experiment of Mr. Young in optics from the beginning of the century and all of that, that's what Maxwell has found, that light is actually a form of electromagnetic radiation, except that he was not restricted into the spectrum for the visible light. He got all of them, X-ray and all the way to the radio waves. So this is basically what this thing in here. So the solution that we're looking at actually is waves, because this is a wave equation, okay? This is for the electric field. We could have done the other way around. By the way, I didn't do it, but you could take this derivative with respect to t and this respect to z and did the same thing. This will be the mixed derivative. This will be the straight out derivative with respect to t, the second derivative. This will be the second derivative with respect to z, and this will be the mixed derivative. So at the end, you're going to find an exact identical equation for the B field. In other words, both of them work together because one of them is responsible for the other. Since now one of them exists, the electric field will have a curling magnetic field, and the magnetic field will have a curling electric field. So both of them are causing the other one to exist. In other words, I cannot isolate one of them, because if I make B equal to 0, E also will go to 0 from this equation. The same thing from this equation, E also goes to 0. In other words, E will not depend on T if B is equal to 0, because its derivative with respect to T will be 0. And also, E will not depend on Z either, because its derivative with respect to Z will be exactly equal to 0. So this E at the end will not exist without B, and vice versa. So these two, they are actually joined at the beginning from where they are formed till this point in here in space where we are. That's why they're called them electromagnetic waves. So these are the wave spectrum that we ended up with. The visible light happened to be in this range, 380 to about 750 nanometers in range. This in this region is the infrared. This region is the microwave. And you can go all the way to radio waves at this point, okay? This is the shorter wavelength, so this is the violet in here, this is the red. And in here you have the UV radiation, ultraviolet radiation, and in here you have a region of the X-rays, and in this region you have the gamma rays. The boundaries between these things are not exactly clear, all of them, okay? Not here because of the human basically limitations. And even we humans with this, we have different perception of colors and things like that. So there is a little bit of distinction. So basically, I can express now the electric field as follows. E is some intensity. I'm choosing this one to be in the X direction. Some intensity of cosine of some wave number K in the Z direction minus omega t. Okay? In the same thing, because that one also satisfies the wave equation, is going to be some wave number cosine of kz minus omega t. In other words, if I take this derivative with respect to z and plug it into equation 1, what is equation 1? So if I take the derivative of ex with respect to z, I'm going to find the following. The derivative of ex with respect to z is going to be minus, I'm going to pull a k in here, k times epsilon naught, times e naught, sorry, and the cosine becomes a sine of kz minus omega t. So I took care of that problem. If I take the derivative with respect to t and plug it into this equation and make them equal to one another, because that's equation 1. So I will have the derivative of b with respect to t, which is by in this case with respect to t. I'm going to look at the signs in here. I'm going to pull out the minus omega first from the get-go. So I have a minus omega, and then I'm going to change the cosine into a negative sign, because when I take the derivative of cosine, it becomes a negative sign. And then I have a b naught times a sine of kz minus omega t. Okay. But the equation, so this becomes a positive. But the equation has a negative to begin with in it. What is the negative? In here, that is Lenz's term actually from Lenz's law. So now I will have a negative Ke naught, and the sign will cancel, so I'm not going to write it down, okay? So it's equal to a negative times a negative times a negative. There are 3 negatives in here. There is one coming from Lenz's law, which is here. And there is another one that is coming from converting the cosine into a sine when we take its derivative with respect to t. And there is a third one coming from actually the chain rule. So at the end, there is one left because you have 3 of them, omega b naught. And again, I'm not bothering with the sign because it's the same factor for both of them. In other words, the time and spatial derivative, the dependence is the same. If one of them is cosine, the other one is cosine. If one of them is sine, the other one is sine. Because if I choose a different choice for the waves, they're going to give me the same expressions for both of them. They have to match because of that sign thing and that. So now the sign cancels, and I have equation 1 simply reduces to Ke E naught is equal to omega B naught, okay? Where omega is somehow related to the frequency of the wave, and K is related to the wave number, to the wavelength of this wave. So this is basically what we're trying to find. What is the relationship between K and omega? We know from physics 4C that omega must be equal to K times the speed of the wave. So we want to check this one. In other words, we want to check that the speed is equal to, if I replace it in terms of wavelength and frequency, also this way. So we call this one dispersion law of physics 4C. Let's see if we end up with the same equation based on these equations. So the second equation tells me a similar story. I have the derivative of b with respect to z. And in this case, I'm going to pull out a minus, again, a minus, similar in the same fashion, k times b naught. So it's going to be minus k times b naught must be equal to, but I have a minus in front of it. So I have to be careful in here. And the minus in here is coming from the curl, actually. So I have to have that. So it's going to be minus times that, because there is a minus also that is coming from the derivative times the other minus. Now in here, I have to take the derivative. First of all, I have a mu naught epsilon naught. What is a mu naught epsilon naught? What is the equation? This one. There is a mu naught epsilon naught times the derivative of Ex with respect to t. Well, first of all, there is the minus that is going to convert the cosine into a sine from the derivative. And there is another minus coming from the chain rule. So I'm going to have two minuses that they cancel each other times omega. So it's going to have a positive at the end, omega times mu naught epsilon naught times the value of E naught. Okay. So this is basically what we ended up with. I can take this B naught in here and sub it into this expression. So this is equation 2 and how it reduces to. Or I can multiply the two equations side by side. So if I multiply them side by side, I will end up with k squared, because k times k is k squared, times B naught squared is equal to, I'm sorry, not B naught squared, B naught E naught, okay, is equal to omega squared. And I have only one of these terms, so mu naught epsilon naught, which is 1 over c squared, by the way. This term itself is 1 over c squared. So I'll have 1 over c squared in here, times, again, E naught, B naught. These two cancel, and they have to be fixed, otherwise we have no solution. If E is equal to 0, B naught is equal to 0, we don't have a solution. So these two cannot be 0, so I can simplify with respect to one another. And if I move c squared to the other side, I will indeed have omega is equal to kc. So that is a confirmation, because omega is positive, k is positive, and c is positive. That's why we only bother with the positive root. In other words, there is a negative root if you want to think about it, but that's for the wave traveling backward. So when this wave hits a medium, it's going to be bounce back, and that is actually, we're going to get the law of reflection of light of a medium, which is something also in physics for C. Anyway, so we have now the dispersion law. There is another relationship which is of extreme importance now. If I take equation 1 or equation 2, it doesn't matter which. So I'm going to take equation 1. It tells me that E naught, so this is just a direct indication from this equation, E naught is equal to omega over k times B naught. And omega over k from this expression is c. So this is equal to CB naught. So E naught over B naught is equal to the speed of light. This is of a very, very important. So for this type of solutions, the strength of the electric field is C times, or 3 times 10 to the power 8 meter per second times greater than that of the magnetic field. So again, we're getting a lot of information in here from these equations just by examining them and basically solving them. So what we found in here is a wave. And if it is a harmonic wave like this one, so these are called the planar, harmonics, okay? So if that's the case, then this is true. First of all, omega is equal to kc, which is the dispersion law. And the second is that the ratio of the electric field over the magnetic field, the c times greater. In other words, that's why our eyes are actually more sensitive to light. And that's why we focus from the get-go on the electric field, because the polarization or the direction where the electric field points is really going to dictate everything for our detection equipment and things like that, because it's c times stronger than the magnetic field. Now let's talk about energy, because we want to see, yes, it's c times stronger, but who brings more energy to the system? We have two fields now in this solution, one for the electric field and one for the magnetic field. So if I want to find the energy density, and I know I made a big fuss over these things when we were doing them earlier in these chapters, we said the energy density in here for the electric field is 1/2 of epsilon naught times E squared, plus that of the magnetic field, which is 1 over 2 mu naught times B squared. So that is what we found. Now, so this is both of them, okay? But I know from here that no matter what, that the electric field is C times greater than B. So this is what I'm going to write. I'm going to sub one of these E's, make it equal to CB, and I'm going to sub one of these B's to make it E over C, and see that there is a symmetry. So this is how the expression for the energy density, remember, this is in joules per cubic meter. So this is an energy density for the entire wave now. So the energy density then, after I take care of that, is going to be 1/2 of epsilon naught times C times EB, from the first term, plus, again, the 2 mu naught in here, and there is a C in the denominator, as you can clearly see, times EB. So in other words, I have an E and B, and I have 1/2 as a common factor. So I'm going to take those out. As a matter of fact, I'm going to take mu naught also out, and C. So I'm going to take this entire term out. So mu is going to be equal to, first of all, the factor 1/2, which is out completely now, times what is left in here is 1, because I already took EB over mu naught C, and 1/2. So I'm left with nothing but 1 in here. But in here, I have epsilon naught times mu naught times C squared. And this number also is 1. This is actually 1, because C squared is equal to 1 over mu naught epsilon naught. So this is 1 plus 1. This is 2, actually. The sum of this 2 is 2. Divided by 2 is 1. So in other words, the electric field, the energy density is just the product of the two fields divided by mu naught C. Because of this fact in here, the contribution, this is from the magnetic field. This is the B field contribution. It contributes 1 to the sum. The magnetic field, the electric field also, contributes the other 1. In other words, there is a 50-50 contribution for both of them. Just the fact that the electric field is C times greater than the magnetic field does not mean much when it comes to the energy. Both of them play an important role when it comes to energy, and they come in 50-50 participation. So 50% this guy, and the other 50% that guy, so that they add up to this quantity. Okay, so this is where we're headed with this one here. So this is what we ended up with. As a matter of fact, if I sub the value of E and B as being E naught B naught divided by mu naught C, and in here I will have a cosine squared of some kz minus omega t. Okay, in all of our observations, omega is equal to 2 pi f, and f frequencies is a huge number, even for the, even for radio waves. Radio waves, if you look at your phone, it's in the gigahertz or megahertz, or at least gigahertz. Okay, it's TV megahertz, so it's a huge. Mega means 10 to the power 6. That means this varies so fast in a single second that all we care about is the average of this quantity. And the average of a cosine squared from the previous chapter, when you average it over one period, so this is actually 1/2. So the average U is going to be just 1/2 of mu naught, E naught, which is the amplitude of the wave, divided by mu naught C. Okay, so this is the amplitude of the electric field, and this is the amplitude of the magnetic field. Sometimes we write it as actually E RMS, B RMS divided by mu naught C, where E RMS and B RMS are the root mean squares, because you just plug in the namely the E RMS is simply equal to E naught over square root of 2, and the B RMS is simply B naught over square root of 2. And now you absorb the 2 in them, and now the expression becomes as such. So now we have an intuition for the energy density, and both of them are actually come up with the same expression here. Mr. Pointing actually was looking at this expression and he recognized something in there. If he takes the cross product of E crossed with B and divided by mu naught, he called this vector, he called it the Pointing vector. He did not call it. People after him called it after him. His name is Pointing, okay? He found that this vector has a peculiar property. For one thing, it points to the direction of propagation, because the electric field is along the x direction. This is along the x direction. This is along the y direction, and the point vector S is along the k hat direction, because of this property in here. In other words, the Pointing vector points, and he did not really intend for that, but that's really how it is. His name is Pointing, okay? Points to the direction of travel of the wave. Furthermore, its magnitude, you can clearly see, has to do with the energy density. Its magnitude is is the energy density divided by C. So the energy is S on average divided by C. In other words, this vector has a lot of properties in here. As a matter of fact, let me talk about the energy first in here. Since we know that if I take the following scenario, let me give you a picture in here, okay? Let's say, for example, I have an area A, okay? And there is a wave coming to it from this side, an EM wave, meaning it's both an electric field and a magnetic field traveling, one of them in the X direction, the other one in the Y direction, and they're traveling in the Z direction. So this is the Z axis, okay? So the wave, if I waited dt amount of time, the one that hits it in here would have traveled this distance. Where c is the speed of light dt. So at dt, this much wave would have passed this area, okay? Which is c dt times the area. That gives me the volume. So the volume now of this space that has already been passed at that point is going to be simply equal to A times C dt, okay? So this is the volume, but I have an energy density of this quantity. Let me go back into the, before I took the average. I have an energy per unit volume this much. So the actual energy that passes after dt, we collect the amount of energy du equals to the energy density times the volume. And the volume in this case is A times C times dt. So this is the amount of volume that we collect at that point. Meaning that if I look at the power now, this is the first P. Meaning that the power, which is the rate at which the energy is basically being delivered, is going to be just U times A times C, where C is the speed of light. And U, you can clearly see, is equal to S over C in general. It's S over C. That is what the energy density is. So then this expression then becomes, the power then becomes S over C times A times C. The C cancels from both of them, and the power then becomes SA. So this is the power. So the Poynting vector has a relationship with the power. As a matter of fact, I can write the following expression. S is equal to P over A. And this becomes what is known as the intensity. Because this is how much power that's spread over an area. So if I have an amount of power, how many watts, that watts will spread all over. So now we have a meaning for this vector, not only the direction, which is the direction of the wave, but it also measures the intensity of the beam, or the intensity of the EM wave. Okay? As a matter of fact, its average is called the intensity. I is the average of S bar, which is the average of the power per unit area. The sun, for example, delivers this much power, 3 times 10 to the power 26 watts. That's how much the sun delivers. If I go outside and look at square meter, how much energy the sun delivers, it's going to be about 1400 watts per meter squared. In other words, if I have a swimming pool 1 meter squared and wait after 1 hour, it's going to deliver so much energy. At the end, the energy is going to divide that by an hour, 3600 seconds, you'll get 1400 watts. In other words, put a thermometer and see how much the temperature increases. So this is the intensity. So the intensity is actually the average of S bar, the average of the Poynting vector. Okay, so we have now a power. The power on average is the area times the intensity. So this is an expression that we will need. Okay. Now here is another thing in here, and this is coming from physics 4D actually, okay? Let me see how we're going to introduce this one, okay? Imagine with me the following scenario. That we have a surface, a physical surface in here, actually, and the energy is coming and rushing to it. So the energy is being delivered to it at the rate of the power, basically, how much power is delivered in there. There is a relationship, and I know that Maxwell had an argument for it, but it's a really long argument for it, where the energy, I use the symbol U for the energy all the way through what for this class, is equal to the momentum of the particle times the speed of light plus mc squared. I'm taking an equation from the next physics when you take. If not, look at the proof for it somewhere else, because it's actually a lot easier to do it this way. In other words, for light, since it does not have mass, this quantity is 0. For the energy, then, is associated with a momentum, and that is the point in here. You're asking, well, the momentum P, so P is the momentum. The momentum is supposed to be mass times energy, times velocity, but I don't have any mass in here. Yes, we don't have any mass, but there is an effective momentum, if you wish. And that effective momentum is the ratio of the energy divided by C. In other words, this is basically the expression that I have in here for my for the electromagnetic waves, okay? So this is the second P. That's the momentum. And I gave it, like, as I said last time, a ponytail. So the momentum P is equal to U over C, the ratio of the energy over C, which means that the rate at which the momentum is changing with time is going to be just 1 over C times the power, because du over dt is just the power. So the change in momentum is equal to 1 over C times the power. This is actually the power, the rate at which the power is changing, that's always power. The rate at which energy is changing, that is always power. This is the force, because from physics 4A, the force is equal to dp over dt. The rate at but I don't have mass. I cannot say m equal ma, but I can say always it's force, the rate at which momentum is changing with time. In other words, if I have a physical, really, physical surface in here, it's going to receive radiation, and that will amount to a force. And this is the force that we're talking about in here. So the force that we have in here is going to be 1 over c. So the force is going to be the power divided by C. So that is another relationship that we need for a lot of our problems. So if they ask you what is the force, if you know what the power is, you're in business. But the power now is related to the intensity times area, or S times A. So remember, this is SA. As a matter of fact, I can write the force as, then in this case, S times A divided by C. C, not S. Okay, divided by C. But I know the pressure, that's the third P, by the way, pressure. And this one will have no leg or no tail or anything like that. So the pressure P, which is really F over A, is simply going to be S over C. This is the surface sitting in there, receiving all the radiation, and it's continuously receiving them, so it's under pressure. For a perfectly reflecting material, the change in momentum is going to be twice, because you hit and bounce back. And this is from physics 4A. So the change in momentum, or the impulse, is going to be twice as much. So this is for an absorbing material. So this is going to be in Pascal, by the way, which is an important relationship that we have. But this relationship is for an absorbing material. For a perfectly reflecting material, the impulse, which is the change in momentum, will be twice as much, because you hit and bounce back. And this is from physics 4A. So you hit and bounce back, so the change in momentum will be twice as much in this case. And because everything will have a 2 in it in here, that will result in a 2 in here, that will result in a 2 in there. So the pressure on a perfectly reflecting material is going to be basically 2S divided by A, by C. Okay, so this is for a perfectly reflecting material. So there will be twice as much pressure, because if you have a metal, you hit it and it bounces back. In this case, it's going to receive twice as much impulse than if you just absorb the radiation. In this case, you get the first change in momentum. You go from, let's say, for example, let's go back into physics 4A a little bit, okay? Let's say, for example, you have 1 kilogram traveling at 10 meters per second, okay? So you go from 1 kilogram, 10 meter, which is the impulse, in this case, 10 kilogram meter per second, and you hit an object in here, and then you stop. It comes to a standstill. So the change in momentum in here goes from this value to 0. So the change in momentum is going to be 0, the final value, minus 10 kilogram meter per second. So this is your impulse. Okay. Whereas if you hit it and bounce back, so basically in this case, you have still your 10 kilogram meter per second coming, hitting the object, but then it bounces back. Since it's a perfect elastic collision here, I'm assuming, so it's going to take 10 kilogram meter per second in the opposite direction. So the object in here, how much impulse it's going to receive, it's going to be basically the change in momentum in here. So the final value is 10 kilogram meter per second in this direction, minus the first one, which was negative because it was in the opposite direction, minus 10 kilogram meter per second. So in this case, it's going to be 20 kilogram meter per second. So it's going to be twice as much. So the impulse is going to be twice as much for a perfectly reflecting material than for a perfectly absorbing material. Anywhere in between them is going to be anywhere between 1 and 2. So this coefficient usually is written as, the pressure in general is written 1 plus R times S over C, where R in this case is the coefficient of reflection, okay? So this is the reflection coefficient, which varies from 0 for perfectly absorbing material to 1, which is a perfectly reflecting material. Okay, 0% reflection means that's completely absorbing. 100% reflection means that it's an ideal reflector. Okay, so this is basically the stuff that we have learned in here. Okay, so this is the pressure, and it's in Pascal. This is the pressure in Pascal. This is the force in Newton. This is the force in Newton also. This is the relationship that we will need, actually, okay, for a lot of our problems. And S, don't forget that S is I. S is I for all practical purposes, because the average, because this is very, very fast, but at the end of the day, it doesn't matter S itself. It's just the intensity of the radiation. And we have how S is related to the pressure, which is, to the power, which is power over area. And the power is basically whatever is given to you. In other words, if you have two basically candles and they have the same luminance, both of them have the same brightness, and you move one very far away, the very far away is radiation will spread over a very long distance, and at the end, the light appears dimmer. That is what the area is coming from, and the area is spread throughout a big sphere, okay? So this is the entire chapter 32 with all of its contents. Make sense? It will not make sense until we do problems, actually. So here is a problem that I'm proposing for you guys to do. One of them is going to be a very hard problem, so I really want to have you guys focus on it. And the others should be not hard to do. So the problems that I have in mind are the following. Problem 22, problem 23, problem 42 is hard. We need to do it, okay? In problem 46 was an exam problem in the past, okay? And similar to it, of course, things don't change. Do change. And problem 44. So what I'm going to do now, I'm going to do these two problems, and this one, and then hopefully we get into that problem, okay? If not, what I'm proposing to do for problem 42, because it's extremely hard, since I did it with another group, so what I'm going to do is probably post the solution for you guys in detail. And if you have any questions or something that's not clear on it, please let me know. Because it combines so many things together to do it. Okay, it combines so many chapters of this class. So Let's get into problem 22. Sounds good?
Sounds good.
Yes, sir.
So problem 22, it's a broadcasting station. It says public station, and I gave you the name for it, in San Francisco, broadcasts a signal at a power. So we're doing 22 at the power of 777 kilowatts. Okay, this is a big, powerful station. I looked at the stations nearby in our region. There is only one station that exceeds this number, and that is actually Channel 5, KTLA. They broadcast at 1,000 kilowatts. The other stations there are within 100 kilowatts, okay? All of them, including Channel 7, Channel 11, all of the other channels. So these are typical numbers, basically. So this is not something to, I mean, this is kind of high, but this is something to basically work with. So in case you have stuff like this one, you should be ready for it. Assume that the wave spreads uniformly onto a sphere, okay, above the ground. So basically here is the powerful station, and here it's broadcasting its signal from an antenna, of course, and its signal is going through a sphere, okay? This is not a circle, it's a sphere. 5 kilometers away is a house, okay? 3 miles away is a house. What average pressure does this wave exert on a totally reflecting surface? So you have metal on the house, and the radiation is coming to hit it. So we want to find the pressure. Because this is a perfectly reflecting surface, we're going to use this expression in here. Where is it? We're going to use this expression in here. This is the pressure, 2S over C. And I don't have S, I need to find it first. So we need to find S. Since we don't have that, we need to find the power. I mean the intensity, and the intensity is the average S. The average S actually, which is the power. And this number actually they didn't tell you specifically, but this is actually an average power, because the average fluctuates up and down. So this is actually an average power. So otherwise I would have to give it to every moment. It's now this, it's now that. It's not. It doesn't make sense. Okay. So this is an average power. So it's the power divided by the area. Since the wave has spread throughout the sphere of radius 5 kilometers, that means the area is 4 pi r squared, where r is this radius, spread throughout a big sphere, hitting, among other things, an object in there sitting on the house. So we want to find the pressure, okay? So we have the intensity I, and if I go back into this expression, all I have to do is multiply that number by 2 and divide it by C, okay? So that's it. So the answer then is going to be basically the pressure, 2 because it's perfectly reflecting, times the intensity, because that's the pointing vector, times I, and I is P bar over A divided by the speed of light. So if I plug in everything, I'm going to find the pressure now in Pascal. So it's going to be P is equal to 2 times 777 kilowatts, and the kilo has a 10 to the power 3 of it, over it, divided by the speed of light, which is 3 times 10 to the power 8, and the area, which is 4 pi, times the radius squared. And the radius squared is 5 kilometers, and a kilometer is 10 to the power 3 squared. I usually take care of the powers first, okay? I have 10 to the power 3 and 10 to the power 3 squared. Or leave it 10 to, okay, so I'm left with 10 to the power 3 out, and I'm done with the powers in here and this one in here, because I had 2 of them. One of them cancels that, and the other one stays. And this 10 to the power 3 and 10 to the power 8, it's 10 to the negative 11. So from the get-go, I have 10 to the negative 11. Now I have to take care of these numbers in here on a calculator. 2 times 777 divided by 3 times 4 pi. Okay, this is the pressure. Okay, this is the pressure. Obviously, 2 times 3, 2 and 4 cancel. I'm left with the 2 in here. 3 times 2 is 6. 700 divided by 6 is roughly about 100. I know I'm getting estimates in here. 100 divided by pi is about what? About 30. So the answer is about 3. And please check your numbers. Check. Oh, this is not the power. What am I writing in here? This is the pressure P. Okay, you have to pay attention to your symbols in here. Check and plug in the numbers, okay? the answer. That's your job, okay? I'm hoping that you have already, everything is ready. You're taking notes and doing this stuff on your own. You're not relying on me. So it's going to be 30 times 10 to the negative 11, and 30 times 10 to the negative 11 is roughly 3 times 10 to the negative 10. Okay, Pascal. Did I do something wrong in here? If not, check this number. Obviously, this may or may not be completely wrong, okay? So you have to check this number in here, Pascal, which is extremely small pressure. Extreme small pressure. That's expected. Radiation. It's not really, compared to the atmospheric pressure, which is 100,000, 101,000 pascals. The atmosphere in you and I that are sitting in right now. So this is a tiny pressure coming from the radiation, okay? So if you think that your drum is going to be punctured just because of this one, you're wrong. The sound that you're hearing from me now is tremendous pressure compared to this one, okay? So it's negligible, okay? That's question 1. Question 2, B. What are the amplitude of the electric field and magnetic field of the wave? So I need to find the strength. Remember I, which is the average of Poynting vector, and Poynting vector, if you guys remember, we defined it as E times B over say mu naught. So it's going to be EB over mu naught. So I can go back in here. Since I already have I is equal to EB, and this is the values in the maximum values, because this is an average divided by 2. Remember, when we average, we take the 2, because the I is actually an average of the Poynting vector. Okay, so normally S by itself is EB divided by mu naught. Okay, since they are perpendicular to one another. But when I take the average, which is S bar, I'm going to pick up in half in here because that's a cosine squared. So it's going to be 2 mu naught times E naught B naught. Or I can write it in terms of the EMSs. So there is a 2 from the average and mu naught in here. This is equal to, again, I can find the electric field if you want me to, just by subbing this value being electric field divided by C. So this expression then becomes E naught squared divided by 2 mu naught C. And from here, we're going to find the E naught, the strength of the magnetic field, as just being 2 mu naught Ci under the square root. And I is just P over A. So this becomes just equal to the square root of 2 mu naught C times the power that was given to us divided by the area A. So if I plug in all of the numbers, I should be able to find the strength of the electric field. And it's a good idea to find this number because we really want to know how strong is the electric field in here. It's going to be 2 times mu naught, which is 4 pi 10 to the negative 7, times C, the speed of light, which is 3 times 10 to the power 8, times the power is 777 kilowatts, divided by the area. The area is 5 squared, which is 25, kilometers, which is 10 to the power 3. When you square it, it's going to be 10 to the power 6. From the get-go, this number and that number cancel, and I am left with a 2 in here. 2 plus 3, that's 5. 5 you subtracted from 7, and you'll be left with a 10 to the negative 2 in here. Okay. So at the end of the day, you will have E naught, which is the square root of 2 times 4, which is 8, by the way, pi times 3, 8 times 3 is 24, actually, I should have written that, times 777 times 10 to the negative 2, so I'm going to place a decimal point in here, divided by 25. And that's it. So let me pull out the calculator in here. Hopefully you're doing the same. You're not relying on my numbers in here. So if I do that, I have the square root of, open parentheses of, I'm going to write it down, 8 pi times 3 times 7.77 divided by 25 and close the parentheses. And that is basically the answer. Did I forget the 3? Yes, I did. No, I did not write it correctly. Sorry about that. So it's 3 times. It's giving me 4.84 voltmeter, which is a very tiny electric field, actually. Electric field. Okay. So that is the value of the electric field. Now, if I want to find the magnetic field, since I found E naught, all I have to do is just divide this one by C. So it's going to be 4.84 divided by 3 times 10 to the power 8. And the answer is going to be some number times 10 to the negative 8. 4 divided by 3 is what? 4.8 divided by 3 is what? 1.2? 10 to the negative 8 Tesla. It's extremely small magnetic field. The point I'm trying to say from this problem is telecommunications does not cause health problems more so than anything else. As a matter of fact, look at the radiation coming from the sun, it's far more electric field in it, far more magnetic field in it. So the thing that people are circulating about this telecommunication causing viruses and COVID-19 and all of that is nonsense, at least from a physics perspective. There is no foundation to it, because if it is, then we have other things to worry about than these things, okay? Because these fields are extremely small. They don't do anything in here. They don't cause even the charges to move, let alone they cause the deformation in the DNA structure or whatever that is, okay? So I don't know. Okay, so we found the electric field and the magnetic field. Part C, what is the energy density of the this wave? What is the average density of the energy this wave carries? So we need to find U bar. U bar, the average energy density, what is it? U bar is just basically the intensity, the pointing vector, which is the intensity in this case divided by C, that's all. Okay. So this number is just basically the intensity divided by C, because in general it's S over C, but when you average it, the average of S is actually the intensity of the wave divided by C. And the intensity, if you remember, is the pressure divided by the area. We should really have calculated this value from the get-go because we keep on hitting it time and again. So this number is going to be what? 777 kilowatts divided by the area, which is 25 times 10 to the power 6. And the speed of light in this case is 3 times 10 to the power 8. Again, plug in the numbers in here and you should find a very small number in joules per cubic meter. Can you handle it? Can you handle these problems on your own, guys? I mean, fixing the numbers and getting the numbers?
Yeah, it seems easy enough for these ones right here.
Sure, sure.
And those who are not live ones, they need to do the same thing because you need to get your hands dirty, okay? You're not in here watching me do things and at the end make mistakes and realize that I gave you the wrong thing. So please fix things, make sure you do them on your own, okay? Because come exam time, you're going to be responsible for things of this nature. D, for the energy density in part C, what percentage is due to the electric field and what percentage is due to the magnetic field? And the answer to that is actually the lecture. It's 50-50, both of them contribute the same amount. Remember, the question is asking you how much is coming from the electric field and how much is coming from the magnetic field. Both of them contribute the same amount for the energy density. For the energy in general, so the answer to question C has nothing, I mean, I could answer that question even without doing a single thing from this one. So the answer to question C is 50-50 each. Okay, so that's the last question. We're doing on time, still have time. So let's do problem 23. Problem 23 says in here, if the eye receives an average intensity greater than 10 to the power 2 watt per meter squared. So if I is greater than this intensity of 10 to the power 2 over 10 to the power 2 watts per meter squared, damage to the retina can occur. So this is a threshold. This value is a threshold for damage in the eye, okay? Okay, I forgot the S in here. Threshold, okay. What is the largest average power in milliwatt that this laser beam? 1.5 millimeter in diameter. Here is the thing. And this is a little different, okay? Don't confuse the areas because that's, so you have a beam now of a laser pointer that is like this, traveling on a long, wait, what is color is this one? So you're looking in here at a laser that is focused over long distance in here, okay? So it stays the same more or less, no matter how far close or far away. So this is basically the width through which the beam is traveling. This is a different beam. So I move it closer or further away. When you look at this one, I mean, you look at a bigger area of green on the screen, but it's not true. It's actually only a small area in there. And that area is of width, diameter. How much is it? 1.5 millimeter. 1.5 millimeter. Okay. Now, if you have the retina is actually a flat surface. When it hits the beam in here, it's going to hit it on a circle whose diameter is 1.5 millimeter. So this is the surface that is impacted, and that surface is that of the circle. And the area of a circle is pi r squared. And r in this case is just the diameter over 2 squared. So the radius in here of this area is just 0.75 millimeter, which is 10 to the negative 3 squared. So you have this much intensity on this much area. So we need to find basically the power. So they want us to find the minimum power that the laser beam can do without causing damage. So if it exceeds that value, it's going to be damaging. So remember, the intensity I is the power over area. From here, we're going to get the power to simply being I times A. And the power then must be not to exceed. So this is an upper limit. This value, which is equal to 10 to the power 2 watts per meter squared times this area in here, which is pi times 0.75 times 10 to the negative 3, the whole thing squared. Obviously, I have the powers in here. I have 10 to the negative 6, and I have 10 to the power 2. So it's going to be 10 to the negative 4. But then I have 0.75 squared times pi. So then the power cannot exceed pi times open parentheses 0.75, and that is squared, actually. It should not be parentheses, but it's fine. Okay, so it's telling me 1.767, and this problem has actually two sig figs. So it's 1.8, 10 to the negative 4 watts, or 0.18 watts, actually, milliwatts. So the power on this laser beam cannot be greater than this much power. So this is the upper limit on that laser device. So when they tell you do not point the laser beam to somebody, it doesn't matter who that person is, it is for a reason, because this can really cause permanent damage. Okay, don't play with this thing. It's really okay. What are the maximum value of the electric field and magnetic field for the beam in part A? So we need to find the E and B again. Since we have I, we can find the electric field. Remember the expression we just found, how I and E is related. So this should give me E naught, since we have I, the intensity already 10 to the power 2. So we don't need to do this because we already found the power. I mean, unless you divide it by that, but it's already I. I is equal to 10 to the power 2. So the electric field from here should be, or this maximum electric field should be 2 mu naught C times I, and you have the I. This is 4 pi 10 to the negative 7. This is 3 times 10 to the power 8, and this is 10 to the power 2 watts per meter squared. You plug in all the numbers, you're going to find the value for E naught. Okay, and you'd be surprised. Actually, it's a big E naught. Okay, let's plug in the numbers and see what we have in here. Because unlike the first one from a casting station, the laser beam is actually focused light, and the electric field will be a lot greater. So let's do this. square root of 2 times 4 pi times 10 to the negative 7 times 3 times 10 to the power 8. From the get-go, this number is actually 10 to the power of positive 1 times I, which is 10 to the power 2. So 10 to the power 1 and 10 to the power 2, that is 1,000 times 3 times 2 times 4, that's 6. 6 times 4 is 24. So it's going to be 24,000, okay, pi under the square root. You see, that's my point. The laser beam is a big number in here, okay, for the electric field. So it's going to be square root of, open parentheses, 24,000 pi, parentheses. So it's 274.58 or 270 because it's 2 sig figs volt per meter. Compare that to the 4 volt per meter that we found for the broadcasting radio station. Obviously, from here, I can find what B naught is because they want also B naught, which is E naught over C. And that is 270 divided by 3 times 10 to the power 8. And you should be able to find what that ratio is. I don't mean to do that twice. I ended up with the same number. Divided by 3, open parentheses, now 3 times 10 to the power 8. Close the parentheses, and the number is 9 or 0.92 microtesla. Okay, it's stronger than the first one, honestly, but it's still a tiny magnetic field, even for laser beam. Okay, so this is. Okay, what's the question now? What are the maximum value of the, so we found them. How much energy would the beam in part A deliver per second? Well, that's the power. So the first question is how much energy per second? It's going to be, remember we found 0.18 microwatts. So it's going to be 0.18 microjoules per second. So it's going to be 0.18 microjoules per second because that's what the watt is. So this question is kind of a free question, it is. Express the damage threshold in watts per centimeter squared. Okay, the damage in watts per centimeter squared. Remember the damage I is 10 to the power 2 watts per meter squared, and they want this number in centimeters squared. So what you do in this case, the meter is 10 to the power 2, 100 centimeters, so it's going to be this much basically. So it's going to be 10 to the power 2 cancels 10 to the power 2. The answer is 0.01 watts per centimeter squared. So this is basically, in a nutshell, all of the numbers basically coming from this problem. Make sense? Okay. Yes. I promise we do problem 42. We're going to do problem 44, and we're going to do problem 46. We are at the end of the period, actually, and we need at least another hour. So what do you guys think if we meet at 5 o'clock and do these problems? And if it needs more time, we'll stay together because it's a lab session. And if it requires less and we're done with them, we're done with them.
Sounds good to me. We can do that at 5.
Yeah.
Yeah. Because if I try to push it, probably too many concepts at once, then we would not do fair justice to them. I know I was hoping that we finish everything, but we can't since we're accountable for this one when it comes exam time. So let's meet at 5 p.m. and hopefully more of your classmates will join us. And especially with problem 42, I really, really want you guys to understand that problem because really it's a practical problem and how to build an antenna actually, okay? Or how antennas work, actually, the principle behind an antenna and tuning and things like that. And as I was saying, these things are potential exam problems, okay? So let's stop the sharing first. And I will stop the recording and I will see you guys in the afternoon, okay?
Sounds good.
See you, Professor.
Mm-hmm.